All right, let's talk about something that's literally all around us. An invisible force that shapes, well, everything, from the weather outside to the phone in your hand to the way you cook your food. We're talking about heat, and more importantly, how it gets from point A to point B. Let's dive in. So, to get our heads in the game, let me ask you something you've probably wondered about. Picture this. It's a cool day, and you're at a park. You see a metal bench and a wooden one right next to it. You touch both, and that metal one feels so much colder, right? But why? And here's the twist. They're both the exact same temperature. No, really. They've both cooled down to match the air around them. So the difference you feel isn't temperature at all. It all comes down to heat transfer. That metal bench is just pulling heat away from your hand way, way faster than the wood is. And that is what we're exploring today. The science of how heat moves. Turns out heat is quite the traveler, and it has three main ways of getting around. Once you understand these three modes of travel, you've unlocked the mystery of the park bench. And a whole lot more. First up, we've got conduction. This is heat transfer by touch. The easiest way to think about it is like a line of dominoes. You tip the first one and it knocks over the next, and so on down the line, right? Well, when one end of an object gets hot, its atoms start vibrating like crazy, bumping into their neighbors and passing that energy along. That's conduction in a nutshell. Next, there's convection. Now, this happens in fluids, so think liquids and gases. Imagine a tiny conveyor belt carrying little packages of heat. A bit of air gets heated up, it becomes less dense, and so it rises, taking its heat with it. Colder, denser air then sinks down to take its place, gets heated, and the whole cycle just keeps going. That's convection for you. And finally, we have radiation. This one's the weird one. It doesn't need any direct contact. It doesn't need any air or water to move through. It's pure energy, just zipping along as electromagnetic waves. Kind of like Wi-Fi, but for heat. It's how the sun warms the earth from millions of miles away, and it's the warmth you feel on your face from a campfire. Okay, so let's circle back to that park bench and take a closer look at our first mode of transport, conduction. This is the world of heat transfer through direct touch. So here's the crucial part. Some materials are amazing at this little atomic chain reaction, and some are just terrible at it. Metals? They're fantastic conductors. They pass heat along super fast. That's why that metal bench feels so cold. It's literally yanking the heat out of your hand at high speed. Wood and plastic, on the other hand, are what we call insulators. They're really slow at transferring heat, which is why they don't feel nearly as cold to the touch. So if we were to have a competition, which metals are the best conductors? A lot of people might guess gold, maybe because it's so valuable, but you'd be wrong. Silver actually takes the gold medal, so to speak. It's followed by copper and then gold. When it comes to pure heat transfer, silver is the undisputed champ. And here's a real mindbender for you. A diamond, because of its perfectly ordered crystal structure, is one of the best thermal conductors on the entire planet, even better than silver. But here's the kicker. It's an awful electrical conductor. This weird combination of properties makes it incredibly useful in high-end electronics, where you need to pull heat away from tiny sensitive parts without causing a short circuit. This same principle explains why those fancy copper pots and pans work so well. Pure copper is a much better heat conductor than, say, brass, which is an alloy of copper and zinc. See, the other atoms in an alloy kind of disrupt that neat chain reaction of vibrations. It's also why the handle on that copper pot is probably made of something else, an alloy or an insulator, so you can actually pick it up without burning your hand. So that's how heat gets around in solids. But what about liquids and gases? Well, for that, we have to leave the world of direct contact and jump into the moving currents of convection. Now, convection can happen all on its own, or we can give it a little push. Think about a radiator in a cold room. It heats up the air right next to it. That hot air rises, and cooler air from across the room sinks to take its place. That creates a natural heating loop. But sometimes we need things to happen faster. That's when we use something like a fan to force the air to move. It's exactly what's happening inside your computer to keep it from overheating. Same principle, just with an extra boost. All right, on to our third and maybe the most fascinating way that heat moves, radiation. This is the heat that can travel right through the empty vacuum of space. So when these invisible energy waves hit an object, one of three things can happen. Some of that energy can be absorbed, which heats the object up. Some of it can be reflected, bouncing off just like light from a mirror. And for some special materials, the energy can just pass right on through, which we call being transmitted. Now, to really wrap our heads around radiation, scientists came up with this ideal concept they call a black body. Just imagine a theoretical object that is a perfect absorber. It soaks up 100% of all the radiation that hits it, no reflection at all. And because of the laws of physics, if you're a perfect absorber, you're also a perfect emitter of radiation. But here's where it gets kind of weird. A black body doesn't actually have to look black to our eyes. A surface like fresh snow is almost a perfect black body when it comes to certain types of long-wave radiation, even though it looks bright white to us. It's all about which wavelengths of energy it's good at absorbing, not just the ones we can see. And this is the key to understanding why hot things glow. As something gets hotter, two things happen. First, it starts radiating way more energy. And second, the type of energy it's radiating changes, shifting to shorter and shorter wavelengths. It's exactly what you see when a blacksmith heats a piece of iron in a forge. It goes from just being hot to glowing a dull red, then a bright orange, and finally to a brilliant white hot. And when I say the energy goes way up, I am not kidding. The relationship is explosive. If you double an object's absolute temperature, it doesn't just radiate twice as much energy. It radiates a staggering 16 times more heat. It's one of the most powerful relationships in all of physics, and it's why things get hot so fast near a fire. Okay, so we know the three ways heat moves: conduction, convection, radiation. So what? Well, this is where the engineering comes in, learning to control that invisible flow to do all sorts of useful things. Here's a classic engineering puzzle for you. Let's say you've got a really hot liquid and a really cold one. You want to use the hot one to heat up the cold one, but they absolutely cannot touch or mix. How would you do it? The answer is a clever device called a heat exchanger. Well, one straightforward design is to just run the two liquids in the same direction, side by side, with a conducting wall between them. The hot fluid comes in on one side, the cold fluid comes in on the same side, and as they flow along together, heat transfers across the wall. It works, sure, but it's not the most efficient way to do it because their temperatures start to even out pretty quickly. But what if we get a little more clever? In a counterflow design, the fluids move in opposite directions. The cold fluid enters where the hot fluid is at its coolest, and they flow past each other. This keeps a much bigger temperature difference between them along the entire length of the pipe, making the heat transfer way more efficient. This simple change in direction is a brilliant piece of engineering that you'll find everywhere, from your car's radiator to your air conditioner to giant power plant. So there you have it. From something as simple as touching a park bench, to the glow of hot metal, to the complex machinery that powers our world, it's all governed by the same three principles: conduction, convection, and radiation. So I'll leave you with this question. Now that you know how heat moves, where do you see its invisible flow being engineered all around you? You'll start noticing it everywhere.